Log on, tune in, find out. Another good idea from Cambridge.
I'll tell you in a moment. It's on slide number 2. Be patient.
Well, you're on there, actually.
Just, yes, it's almost invisible on that. You know, colours are always a bit of a gamble with these. I wasn't quite sure who the audience was going to be, so I hope it's not going to be something that you know everything about already, but I thought I'd give a talk which is sort of a two-part talk, as you'll see. One part, I'm just going to describe long-range forecast systems in general, thinking of a couple of general circulation model sort, and saying a little bit about the one that's used at the Met Office at the moment, and something about how you decide how good or bad the model is, and how you might try and convince other people that the products that come out of them are actually worth putting into action. And the second part of the talk will go from the very complicated extreme models to the very simple extreme models. I just wanted to describe to you really one of the common simple models of the ENSO phenomenon, and just say a little bit about what happens when you look at some variations of some of the physical constants inside that model, and see if maybe that sheds a bit of light on what happens when you start changing the climatic state and the greenhouse gas warming. Okay, so I've pretty much said all this already. Two parts. One, long-range forecasting, a sort of description of the ingredients that go into one of these multi-model ensemble schemes, which is of course is relevant to the sort of design of greenhouse gas type experiments, with the advantage, or perhaps the disadvantage, that because these are only seasonal range experiments, by making a series of hindcasts or retrospective forecasts, you can test your model against reality and decide whether A, the model or B, the various strategies that you're using to correct the model are actually of real benefit or not. Okay, and my thanks to the long-range forecasting team, of course. From the GCM side, much of what I'll show you comes from really based on the work by the teams there on developing the forecast systems and products. A little bit about myself, the man in the front who seems to want to know who I am. I've got a background in geophysical fluid dynamics. I've actually been at the Met Office thinking about this since 1985, which is a scary thought. Much of that time I've been working on models of various complexity, statistical and intermediate and general circulation type, and I realised in that sort of 20 odd years the subject has gone the whole range from using quite simple models to try and understand why ENSO oscillated at all, right through to implementing full-blown operational systems rather akin to weather prediction systems, and all that entails with assimilation of ocean and atmosphere data, creating products, running to schedules, and all the rest. The whole subject has evolved from early exploratory beginnings right through to, as I'll describe to you, full-blown operational status in the weather forecasting world. And also, why have I got Met Office and UCL on my slide at the front? Actually now, in the last few years, I've worked part-time, half-time in Met Office in the long-range forecast group, and half-time in UCL mathematics department, where I supervise some students who are trying to develop simple models on various aspects. I just mentioned a couple of them here. One's initialization, one on the so-called re-emergence phenomenon. And some of the work that I was showing you later on in the talk it's got some relationship to the initialization work that's done with one of my students, Jamie Jackson. Okay, so first up, what is the present state of seasonal prediction systems really? Some of you will know this already, but I thought in the context again, people are usually aware of what goes into a long range, into a greenhouse gas type system, but not so many people are aware of what goes into the seasonal forecast systems, which lie in between the weather range and the greenhouse gas range. So the sort of ingredients, typical ingredients in a couple of GCMs, of course, an atmospheric and an oceanic general circulation model, which tend to be very similar configurations actually to the ones which are used in the greenhouse gas experiments. We're talking about a resolution of the order of 1 degree by 1 degree. Models these days pretty much all have enhanced tropical ocean resolution, because getting a decent ENSO representation is, of course, particularly for seasonal forecasting purposes, is of paramount importance. So you really need to represent the ocean dynamics that underlie such events. Sea ice, some models use statistical sea ice, some use dynamical sea ice. That's a sort of an area under development. Yes?
Sorry, just a quick question. The enhanced tropical ocean resolution, does that happen both longitudinally and latitudinally, or does it primarily happen longitudinally?
It's enhanced, north-south resolution, typically enhanced down to about a third of a quarter degree or so. East-west, in the very early days, we actually had a model which had higher resolution in the eastern and western Pacific, but I think that's not, we're not aware of any models that actually use that option now. We used that back in the days when you had just a tropical Pacific Ocean. You could afford to do that, and it's much trickier to implement unless you've got a very fancy grid scheme in your model to enhance the resolution in both directions. Can be done, of course. So it means you lose out on coastal upwellings and the like. We're aware of that. Yeah.
What about depth? I mean, how many levels in
I'll tell you that in a moment. Typically 20 or 30 odd levels at the moment. In fact, that's the next one on the list. Is it stratosphere resolving or not? Preferably yes, but it does cost, so some models do and some models don't. I think it's probably true to say at the moment most models don't properly resolve the stratosphere. There's a few levels up above the tropopause to allow a stratosphere to exist, but it's not really very dynamically accurate. But we're sort of aware that you would like to have dynamical accuracy up there as well to allow these tropical to stratosphere down to the exotropics type cycles to take place. Greenhouse gases, preferable again. You'd like to have the greenhouse gases changing even in the seasonal model, because as we'll see, if you want to test the model over a couple of decades, then really you ought to allow the greenhouse gases to evolve in the model over that time scale. It does make a difference whether you allow the greenhouse gases to evolve or whether you keep them fixed and constant right throughout the whole range of hindcasts that you do. Initial conditions, using data assimilation but not directly in the models, because what tends to happen is that you take an atmospheric analysis from somewhere else, usually another atmosphere model, maybe not even of the same class as the one that we're using, so there's a certain amount of extrapolation going on there. You need an ocean analysis to initialize the ocean. Again, that's done separately from the coupled GCM that you're going to use, but usually with the same ocean this time, so at least that's an advantage. You'd really like coupled data assimilation between the ocean and the atmosphere. Very difficult. There are what you might call quasi-coupled schemes beginning to evolve, and that's a topic where that's evolving fairly quickly. Most people would like to implement some sort of quasi-coupled scheme. It's sort of research in progress. It hasn't really appeared in the operational models. More ingredients. You generally want to have a pretty broad sample of what's going to happen next. So you might say, I guess a typical number again is something like 40 ensembles, quite a large one to try and get the best sample of the probability density functions in the future. To do that, there are various strategies that you can use. You can perhaps perturb the initial conditions. You could stagger the start times, in other words, start your forecast on successive days just to change initial conditions in a realistic way slightly. You might want to include some sort of stochastic effects inside the model, and you might want to say, well, I realise my model isn't the ideal one. There may be a similar model with slightly different parameters, which is indistinguishable from my model, but gives a different forecast. So you try and represent model uncertainty to some extent, perhaps by varying the actual physical parameters inside the parameterizations in the model. And of course, you run against the problem that if you run the model ahead more than quite a short time, the seasonal forecast, you want to run ahead at least a couple of seasons. The models all drift towards their own climate. Again, there's a couple of sorts of fixes you can use. You've got to fix it somehow. Just putting out the raw forecast from the model would be quite misleading in the presence of this sort of drift. So, one strategy is to simply run a large number of hindcasts, see statistically where did you go wrong, and simply correct it statistically. Or another strategy, which is actually used in the Met Office decadal prediction system at the moment, which I should mention, is that you use anomalies from the model climatology. So the model isn't going to drift towards its own climatology because it starts from its own climatology. Both those strategies have their advantages and disadvantages, and it's by no means clear which one is preferable.
So, in a couple of seasons forecast,
Yep.
what then becomes the definition of the drifted climatology about which you calculate the anomaly?
Yep. Let me see if I've got here's a picture. Here's drift in an old picture of drift. There are more up-to-date ones around. This is enough to give you the sort of idea of what is going on. This is the equatorial Pacific, and the various coloured lines. The top figure shows the difference between the forecast and the actual observed climatology. So you take a large number of hindcasts over a number of years, work out a model climatology from the hindcast. It differs from month to month because the model's drifting away from, you constrained it to the real world when you started the forecast through data assimilation offline. You then let the forecast go, the model wants to gradually drift off towards its own climate. And this drift can be quite substantial. You can see on that diagram there, see if I can point to one. Perhaps we look at the bottom one, you can't quite see it. That dotted line there is the observed annual cycle. It's run over a bit more than a month, more than a year to make it clear. And you can see that the models all drift away from where they should be, and some of them drift quite dramatically away. In the course of 2 or 3 months, they might drift, in some cases, 2 or 3 or 4 degrees. The sea surface temperature we're looking at 2 or 3 or 4 degrees away from where they should be. So the simplest way of correcting your forecast is simply, is simply to say, okay, I can estimate what that difference is and simply subtract it from my forecast. And it's probably the method that's used most commonly at the moment. It's simple, it's certainly very helpful to do so. It may not by any means be statistically the optimal way to do that sort of correction. But you've only got a sample of not many years, I'll say more about that in a moment, to base these corrections on, so you can't really afford to do anything terribly fancy when you're making these corrections.
So I guess my question was...
So, did I answer the question? No.
No, I mean, I would expect that the models would produce from the ensemble, an ensemble mean climatology. That would be the basis of the anomaly construction.
Ah, right.
And it doesn't sound like that's what you just said.
No, because except for special places like ENSO, you don't actually want to put out an ensemble mean forecast. You're
interested in anomalies.
Well, let's see if we're talking about the same sort of anomaly. There's an anomaly from the observed climate that you expect for that particular place in that time of year, which is what usually people want to find out about. And you want to say what is the expected anomaly, what's the sort of range of conditions for that particular place and time. And the other sort of anomaly, I guess, relates to the spread in the forecast. How much does the ensemble, what's the anomaly of the ensemble itself from its own mean, okay, which is really measuring, have the forecast just got a very broad scatter in which case they're not really actually telling you very much, or are they, quite closely confined to each other, in which case you're fairly confident the models ensembles at least all agree with each other. And it doesn't necessarily say it agrees with the real world, but at least it gives you some confidence that at that time the model isn't producing a large amount of scatter inherently. Yep, all right. well, okay, model drift you need to take into account. Just one example of the ensemble, you can find endless pictures of this sort. This is on our own particular website. Oh, bother. Bear with me, I'm going the wrong way. Right, let's look at this before I press the button. Okay, various forecasts you can find on our own website. These are the ENSO plumes. The latest one suggests that this current La Nina is going to keep on going. In this particular case, there's not very much spread on this ensemble. I just picked this one because you can actually see in these plumes, which are only usually shown for the ENSO, not for other variables. You can get some idea of the spread of the ensemble within that. And here, this particular forecast is fairly confident of its own skill. This is the forecast from, okay, which one is which? That's the October one is that one, and the April one is that one down there. I'll swap the labels around. This is what actually happened, and this is a fairly predictable situation, of course, where most models, including ours, were fairly confident and in general giving the right guidelines in saying that there was going to be a switch from the El Nino to the La Nina type conditions in the Central Pacific region. Okay, I should mention here, this is what I was showing you was a sample taken from an European Union project called Demeter, which finished a few years ago now. It's been replaced by the Ensembles project, which is also just finished, which more later. The general idea under both of those projects was to take several different coupled general circulation models, run a substantial hindcast set from them, and try and assess what the actual skills and relative skills of the systems were. Okay, so again, the idea of producing these hindcasts, or reforecasts, retrospective forecasts, as they're variously called, you really want to run the same system, the one you're using to make the forecast, over the last few years, as much as you can sensibly afford with your system, really, usually tens, usually with a smaller ensemble, because you can't really afford to make a 40 ensemble every month for the last few years. And that sort of information what you need to estimate what the model biases are. We're just looking at the bias in the tropical Pacific, but of course you want to know what the bias is for every variable that you're going to make a forecast for. And you also want to use it not just to find out how good the model is by looking at the biases, you want to estimate how good the model is at making forecasts. And again, at least in seasonal forecasting, you can build up a sufficient number of these, you can make some statistically sensible estimates of the model's own skill, which is very useful, in fact, because, as I said, the models used in seasonal forecasting bear a lot of resemblance to the ones which are used for climate change prediction as well. So these provide a very good test against reality, if you like, of the performances of these various coupled models. It's not a perfect situation because, of course, you know, the climate's not stationary. There are trends, there's decadal variability, which you have to take into account, and you also face the problem that the observing systems which you're using to start the forecasts, they're also changing in time. They change in coverage, they change in the sort of instruments that are being used to accumulate the data which is used to make the forecasts. So you have to take the sort of information that you get out of this process with a little bit of skepticism, I suppose. You can't take it too literally that the skill that you see is exactly the skill of the forecast system itself, but it does give you pretty good guidance as to what it might be. The current state of the art, they're actually, in the last few years, this seasonal forecasting business has been gradually getting itself more and more organised and with increased collaboration with each other. WMO has decided to implement these so-called global producing centres, and there are now, the numbers gradually increasing. With the number earlier on this year, they're up to 12 various systems. Oops, I must not do that. Some of which are coupled general circulation models, some of which are the so-called two-tier models. In other words, you're not running the system fully coupled, but you're making a prediction of the ocean separately, and then you're making a prediction with perhaps a high resolution atmosphere beyond, using the information you've gathered from the individual ocean forecast, which might be statistical in nature, or it might be dynamical in nature. But there are indeed now 12 such systems, which are all the global centres. They're all producing global forecasts, they're all producing products with global coverage, which you can find at various places on the internet. So it's becoming a complex business, really, to keep track of all these forecasts, I must say. And there are efforts underway to try and make sense, combined sense of all the information that's coming out of all these centres now. And of course, I should mention, these are just the ones which WMO has put on their designated list. There are, of course, several other producers of global forecast information as well, which don't make that list, but nevertheless play an important role in the seasonal forecast business. Just to give you some idea of what's in our own system, we've been running coupled general circulation models in the Met Office now for getting on for 10 years, actually. We've evolved, GLOSSY stands for global seasonal. We've just evolved up to GLOSSY 4. Obviously we've been through GLOSSY 1, GLOSSY 2 and GLOSSY 3 in that stage. Having just developed a new system by Alberto Arribas and his team at the Met Office. That went operational about this time last year, and they've just finished submitting a paper which describes that system and its performance in some detail. So if anybody really wants to find out the nuts and bolts of what's inside and how it works, then there is a description available. But actually the model at the moment is using one of the latest Hadley Centre climate type of model called HADGEM. 38 levels in this particular one, so it represents the stratosphere but doesn't resolve the stratosphere. That's an issue that's being addressed at the moment as to whether the model can be upgraded to add more levels, particularly in the stratospheric region. The ocean remains about 1 degree resolution, enhanced equatorial resolution. 42 levels in that case certainly seems to be sufficient for the purpose. Actually, most of that lies in the upper ocean. The atmospheric model has got a couple of interesting features in it. One is the use of random parameters within the seasonal forecasting model. That's a new feature for GLOSSY 4. The previous models didn't have that. And this is the system whereby you allow some of the parameters in the atmospheric physics to vary within the forecast model. And also from the stochastic.
The parameters vary in time, or do they stay constant for a run and vary across ensemble members?
I must admit I don't remember the answer to that, but I won't guess. I'll mislead you if I try and tell you what it is. And the other one, it's a scheme that's been used in the medium range forecast system for a while. So the seasonal forecast system is, in some senses, becoming more compatible with the shorter range schemes in putting this sort of feature in, and also sort of taking advantage of development work that's done for medium range systems. We can just actually pick up one of these schemes, and because we're using fundamentally the same dynamical core in all these models, you can simply pick up these features and just turn them on. Not quite that simple, but you get the idea. And the other one is there's a stochastic backscatter scheme within the model as well. And this is what really generates the spread inside these forecasts. We use a 42 ensemble at the moment. It's made up of running 14 per week. The 14 which start each week all start from the same initial conditions, and their scatter is entirely due to the, don't do that, entirely due to the internal stochastics in the model. Yes?
Have you noticed whether or not the stochastic kinetic energy backscatter scheme actually makes a difference in the mean?
I'm not sure we would have enough information with and without to be able to answer that question, frankly. Somebody probably knows, so I don't know the answer, but I probably know somebody who does. Put it that way. I really want to find out.
I'll ask Judith.
Okay, now typically the problem is that you run a set of trials with the model and you don't really run it with and without to see what the difference is. You turn the scheme on, you run it and say, oh, that's performing well, we'll keep that in. Then, of course, having run the system, you need to make some forecast products out of all this. And typically, you do that once a month. Typically, a whole range of different sorts of maps, indices, values come out of these. Mostly for meteorological purposes, and they seem to be rather generic in nature. There are a few special purpose forecasts that come out as well, which are designed for particular applications or customers, if you like to put it that way. What I thought I should mention is that out of dynamical seasonal forecasts these days, several centres now routinely put out, this is the Atlantic tropical storm forecast. We produce one of these before each year. We've done so for the last few years, just to give the impression that it's not just ENSO that these models are all about. You can actually, in principle, forecast a huge number of different things. In practice, you only have time to concentrate on a few of them, the ones that other people have got some demand for, or they're quite broad, generic type products, giving a broad range of information. But quite pleased with these though, which is why I'm showing it. The tropic storm forecasts have actually been quite good. Their track record has been good over the last few years, in line with most other Atlantic storm predictors. We predicted quite an active season for this year, simply because there was a couple of factors, the La Nina for one, that were saying, let's look out, there really ought to be enhanced storm activity. That has indeed taken place, and you can imagine people are quite interested in getting that sort of information. The multi-model. Again, this is kind of relevant to the sort of work that goes on with the climate change models, where people are now very interested in how do you combine the information from several different sources, several different modelling sources, to the best advantage. And again, the seasonal forecasting world started doing this some time ago. There was, this wasn't the first one, but it was one of the early ones. Again, the Demeter project, starting 10 odd years ago, with a couple of GCMs being run in a coordinated way, are able to combine the information from them and test out various multi-model strategies. And it did turn out, of course, as everybody knows now, that the skill is better by most measures if you combine the model from several different sources rather than relying on just one model, or perhaps a big ensemble from one model. Because the models do differ quite substantially in their inherent features, it is worth them. They do give enough different samples in the future that it's worth combining them together. They don't all look the same, and they don't all sort of point off in the wrong direction. They tend to scatter around the right direction, if that makes any sense. Anyway, there are several articles being published now. These are some of the first that I mentioned. There have been quite a lot since on combining models. And of course, there's been a lot of interest in this, and the statisticians have been busy trying to combine this information together in lots of different ways. You can imagine you can calculate any number of skills from the models, and you can try perhaps weighting the model, saying I'll put the most weight and the model's got the most skill for this variable for this particular place and time. It turns out, so far anyway, it's actually quite hard to beat the simple equal weights sort of approach, as long as the models that you include in your basket are all performing incredibly, shall we say, then the size of sample that you've got makes it hard to justify taking a too fancy a statistical approach at the moment in trying to combine the information together. Here's one example. As I said, this is an operational multi-model. It's been running for 3 or 4 years now, which is the Met Office and the European Centre in Renning and Météo France all run their operational seasonal forecast models in some sort of synchronization, and there's an operational production now of the forecasts from those. You can see them on the internet. And it's also a chance to describe a sort of typical product that comes out of this. The probability forecast. This one is the forecast for January, February, March for 2011. So it's a real live forecast. And this one is sort of summary picture, which is commonly used where you try to summarize pardon me. You try and summarize the probability information in one diagram for the ease of presentation. So this is a map just for the 30 north to 30 south around the globe, and it's really indicating one, which is the most probable tercile, sort of above normal, near normal, below normal tercile approach, and how likely is it, given you know which one it is. Of course, we have the situation of the cold anomalies in the equatorial Pacific Ocean reflected in the air temperatures immediately above. So of course this region is a region where there's quite very high probabilities that you're going to be the bottom tercile, but scattered around the globe. You can also see regions where the air temperature is predicted to be with some high probability in the upper tercile as well. So that's a typical sort of product that comes out of these forecast systems. Maps often presented in terms of a few categories, 3, 5 categories, sometimes more, and mostly in this probabilistic type of format. So not deterministic, not saying we think this is going to happen. The ENSO plumes are deterministic in the sense that they give you a fairly good idea of exactly what's going to happen. More usefully, it turns out, people have done sort of value assessments on probabilistic type formats. It's more useful to use a spread of information rather than just one particular value. And again, the WMO has been active in trying to coordinate all of this. So there is actually now a website where multi-model forecasts are available from all these global producing centres. So increasingly there's coordinated information being produced on the seasonal scale from these GCMs, and hopefully soon there'll be sort of do-it-yourself sites as well, where you don't have to take their word for it as to what the best combination model is. You can create your own, and that's of course useful because if you're not interested in a generic combination of all the models, you want to know what's going to happen in my part of the world in the particular time that I want to know about it, and you want to have a particular combination of models to give you the best forecast for that particular bit of information. Okay, communication, perhaps I'll just skip through this, but just to say that communicating forecast is one of the becoming increasingly important aspects of what you do, so people are continually looking for better ways. How do you tell somebody else what the forecast is in such a way that they're actually going to make use of the forecast? And again, these regional climate outlook fora have been developed in various parts of the world, where effectively it's another sort of multi-model. It's a multi-model where a group of people sit around a table and try and convince each other that their forecast is the one to believe in some senses. But the system works. People do come to an agreement at these meetings on the probabilities of, in these cases, the probability of rainfall in advance of some rainfall season in various parts of the world. And again, there's a website, you can look that up, so I won't dwell on that too much. This is just an example, just to show you a broad idea of the format. You can see what people, people try and group together somewhat subjectively the geographical areas where they think the rainfall is going to have a similar sort of probability distribution in the future. Something that's a little bit hard to automate, and it does require, well, perhaps best done with people sitting around the table using their local knowledge to try and draw that map to their best knowledge. How do you convince other people to use it? Don't want to dwell too much on this. Again, this is using hindcasts just to get some idea of how well a model performs. You can find endless examples on the internet. One you can find a large number of examples, a lot of different variables, a lot of different skill scores came out of this EU Ensembles project. The ones which I find quite informative, ones which don't actually involve calculating a score at all, but they simply illustrate what happened and what the forecast model thought should happen. This is for an ENSO 3, in fact. It's a very skillful area. As you know, the red blobs, red dots are the observations, the blue ones are the ensemble means out of a multi-model again, and the green bars simply give you an idea of the spread of the forecast. And like a lot of similar systems, there's quite a lot of skill to be had even when you're forecasting, in this case, 5 to 7 months ahead. Not so easy when you look at some other parts, of course. This is trying to predict the North Atlantic Oscillation. It's a much harder target, of course. And here, of course, you can see there's a lot of spread in the ensemble. The blue forecasts, because there's such a lot of, the models aren't very decided on which direction they should go, so the mean looks quite flat compared to the variability that's in the observed behaviour. The skill isn't 0, the correlation is actually 0.2 on that map, but it's low. Which raises, of course, the question, what's actually the limit of predictability here? Or should the model actually, is this what this is the best the forecast models can do? Is the NAO inherently unpredictable, and this correlation of 0.2 is in some senses the best you can do? We obviously think you can do better. There's obviously room for improvement, but it's a little bit hard to judge how much better should you expect the model to do for a hard target like the North Atlantic Oscillation.
You know how much that has to do with initial conditions, and that you might have more in the tropical Pacific, or
It's no, I think it's the answer to that, but do the models retain the information that's in the initial conditions is one of the challenges, of course. There's a lot of inherent NEO activity inside an atmospheric GCM, regardless of whether it's coupled to anything else or not. We sort of believe that NAO is skillful to some extent. So there is some information in the initial conditions, partly in the upper ocean conditions that you've got. For the first few weeks of the forecast, maybe there's some information also in the dynamical state of the atmosphere when you start out. Okay, how much the model can retain that? Well, what's the upper limit on the predictability? I think we'd really like to know, and there are various projects around to try and evaluate what the upper limits are and find out what's missing in these models in trying to predict these harder targets, shall we say.
I suppose that issue about predictability, if you had a really good system, shouldn't it actually tell you it can't predict it by widening out its own uncertainty?
Yes, the statisticians looked at this sort of thing. Does the spread in the forecast tell you anything about the skill of the forecast? Is one way. Not always, the answer to that.
I mean, that's why I said in an ideal system, in an ideal world, isn't that what would happen?
Oh, in an ideal system, your forecast PDF should be the actual, if there's such a thing as a perfect forecast PDF, it should be the forecast PDF, and its spread should represent exactly the uncertainty at that time and place, yes. Okay, I spent a little bit more time than I should have explaining what the current systems are. I wanted to go to the other extreme of ENSO models, as it were. You can predict ENSO with some extremely complicated models. You can also try and understand ENSO with some far simpler models. I just want to briefly run through one particular model. They're helpful in many ways. They help you understand how ENSO works. They're potentially tools to help you assess whether your big complicated model is doing what it should be doing, and you can obviously measure your big complicated model against the observed world, but you really like to have some sort of mechanistic view of what's going on inside the model, which isn't so easy to get directly from just looking at the model and the observations together. And the simple models also provide easy to run tools, if you like, for asking what if questions. What if the sea surface temperature warms up a lot and the global warming, for example. Again, I think most people are probably familiar with the ingredients of these, but a simple typical model for ENSO, you want to simply represent a wind-driven ocean, typically with what a reduced gravity ocean. Linear dynamics is usually good enough on an equatorial beta plane, captures most of the essential features that you want to with this degree of simplicity. You want some sort of representation of the dynamics of the temperature at the surface, representing upwelling, advection, simple exchange with the surface, and a typical atmospheric model is usually statistical in nature. It says that given the sea surface temperature, there's some rule which tells me what the surface winds that drive the ocean are going to be as a result. They can be ranged from statistical models with a few EOFs in them, for example, or the very simple ones simply say, let there be a wind anomaly which is proportional to the sea surface temperature anomaly, and for simple modelling purposes, that's good enough. Okay, so yes, we want a east-west thermocline and surface temperature layer, perhaps a mixed layer at the surface, and some sort of perturbation to the thermocline. And the simplest model is the one that was developed by Jin some years ago now. Simple enough, you can solve it analytically. The advantage being that it's nice and easy to understand what's going on inside the model, and yet it has lots of interesting features that seem to represent what goes on inside the real world ENSO. And you would hope that if you try to apply such a model to your GCM, then it might similarly provide you some insights as to whether your model is behaving like a real world model or real world or not. So his approach was just to reduce the ocean down to a few representative boxes in the equatorial area, in the off-equatorial region, and take averages over, say, the East Pacific, East Equatorial, West Equatorial Pacific, and you would have one temperature variable to represent what's going on in the equatorial Pacific, and you would have some representation, a wind anomaly proportional to that temperature anomaly, which influenced not just the equatorial region. I've drawn this big circle because the winds with the atmospheric radius of deformation extend well off the equator and influence what's going on in the off-equatorial regions as well. Okay, so in the simple model, wind stress simply proportional to the temperature at the equator with some coupling coefficient, it's called C. And one of the simplifying insights that they had was to simply say, well, in the equator, we know there are relatively fast Kelvin waves running along the equator, but if you're taking an ENSO point of view, then perhaps you can ignore that as a fast process and simply let the ocean equatorial strip be in balance. In other words, the thermocline tilt is in balance with the wind stress induced anomaly, in turn proportional to the temperature there. But of course, you can ask, well, is that a reasonable thing to do or not? And of course, you can go back to the observation and ask, are wind stresses really proportional to temperatures in the equatorial strip? There's a recent publication by Kim and Jin, where they've done that, they've checked both in observations and in a set of couple of GCMs as to whether these simple approximations are actually credible or not. Obviously, if those sorts of proportional representations aren't credible, then your simple model has a fair bit of doubt cast on it. But of course, since they've made some progress with this, by and large, the sort of balances that they assume do actually hold up. Yeah.
Which T is it? T east or T west?
It's T Central East in the equatorial Pacific. Where you choose to measure your T actually differs from model to model. And you have to be a little bit careful because models don't always put their ENSO variability in the same place. That's something you have to be aware of in trying to calculate these balances.
Well, there are those people who complain that the Eastern Pacific is the place that's least sensitive because of the Clausius-Clapeyron equation.
Under
And so any
Big
dynamical
hit for
linkages,
ENSO dynamics.
atmosphere dynamical linkages should really
Oh
be
yeah, sure. We've done that. We did this quite recently actually. Looked along the equatorial strip and asked how well do these two relate to each other? And yeah, if you go right across to the Eastern Pacific, you get a picture that looks like that actually. You get this big fuzzy ball where the wind stress anomalies don't seem to bear any relation to the temperature anomalies at all in that part. But we did that in our particular model. We found that mostly it looked more like this across most of the Pacific. There's a decent linear relationship with not negligible amount of scatter, but to a good approximation, it's a linear relationship between the wind stress anomaly and the temperature anomaly. When you get across the West Pacific, same thing applies. It starts looking like a big fuzzy ball again, instead of anything that looks like a linear relation. But across enough of the Pacific, it's sufficiently linear that the large-scale balance probably holds good. So I think that's probably a credible assumption to make. This is the observed world. This is wind stress against temperature anomaly. You can't quite see the line of fit. It's fairly fuzzy from the observations, but there is, I guess, a statistically significant linear relationship between the two, and a pretty broad range of behaviour between different models, it has to be said. I won't go into the details of that. Okay, skip that. You have Rossby waves driven by these equatorial by wind stresses, which effectively link to the equatorial temperatures. That's all I need to say. Rossby waves are, again, I just picked that example because we looked for the Rossby waves in our own model recently. It's one of the versions of the Hadley Centre model. Look in some place like the Northern Strip, and you do indeed find fairly clear representations of the time and years going up here. These interannual scale Rossby waves do indeed seem to be a dominant feature of our model ocean, and similar pictures hold for the observations. So that's a credible feature. Let's just say, with lots of assumptions, you can take the surface temperature equation, linearize it, put in a load of physical constants such as the background horizontal temperature gradient, vertical temperature gradient, the amount of upwelling you've got, and the background currents in the model. That one doesn't matter, but the zonal climatological currents do matter in these sorts of models. We skip the detail and just say that typically these and several other variants of the same sort of model come down to just solving a couple of coupled ODEs which contain a whole bunch of constants which are all eventually just combinations of all these various physical parameters, a coupling coefficient, the depth of the ocean, the stratification, the background upwelling, etc., etc.
And what is the source of the nonlinearity there? The hyperbolic tangent?
Yep, I skipped it over, but in this particular one, it's just saying, in linear speak, the deeper the thermocline, the higher the temperature that you're upwelling, but there is a limit to how much that upwell temperature can vary, and the hyperbolic tangent is the mathematician's common representation of how to deal with that particular feature. It just means that in the linear model you can have a damped growing oscillation. If it turns out to be a growing oscillation, you can sort of keep a lid on it by having some sort of nonlinearity in the system. There are various places you can put it in, but this is perhaps the commonly accepted simplest nonlinearity that you can put into these sorts of models. Okay, and having built your model, you can then divide it up into a bunch of parameter regimes, which are, I think, interesting to look at. At least it's the sort of view that I'll show you in a moment. I think it's interesting to look at these, how the regimes of behavior shift as you change constants within the model. These two values, P and Q, are just, again, combinations of physical constants. They're just convenient axes to use. And you can divide your regimes up into a stable regime. The model might be oscillating, but it's a damped oscillation. An unstable regime, we've got growing modes. What I've called an unstable multiple regime, where it's unstable, but it might go off to oscillate around some non-zero state as a possibility, or it might oscillate around to different non-zero states. And a stable multiple state where the model is unstable to perturbations from its rest state, if you like, but it will head off to some other stable equilibrium and not oscillate at all. Okay, so effectively this regime is simply oscillating around the multiple states that exist in this regime. Okay, and then you can play the game of varying parameters in the model. So this is one where we varied, again, people commonly do this, varying the coupling coefficient. The coupling coefficient C is varied over a range of plausible values. And on this diagram, I should say that the reference state here is turned out to be some unstable state. So what I've done is pick a stable state, and this PQ diagram, this is the unstable region here, and we started at that point there and varied only the coupling coefficient. Everything else was held constant in the model. And if you do that in this particular case, for a small value of the coupling coefficient, no great surprise, the model is stable, and then at some point passes a critical value where it becomes unstable, and you get an oscillating ENSO whose amplitude is quite sensitive actually to the coupling coefficient at that point. And the period, again, which seems quite sensitive to the actual value you choose for the coupling coefficient. One of the interesting things you find out, this sorts of model is very sensitive for some parameters and very unsensitive for other parameters. I won't go into all the details of that, but that's been one of the sort of interesting features to explore in this particular model. If you take this regime view, that's what I call the PQ diagram, and we started out here, didn't put an arrow on this one, but effectively for low coupling, you start out in a stable regime, the model goes unstable, passes through the unstable linear regime. If you keep on increasing the coupling coefficient, it actually heads off into what you call multiple unstable regime, and if you increase it beyond this point, it actually goes into, in this particular model, a rather unrealistic stable state, which is, so the ENSO oscillation stopped, you flipped into another climate effectively in this particular model. No stochastic forcing, I should say, in this particular model. People might argue they should have stochastic forcing in it. So we did some experiments by putting stochastic forcing in, just to see what effect that would have. This was done by Warren O'Neill, who was did a summer project at UCL, and you can't quite see what's going on here, but again, this is the amplitude of the ENSO oscillation that you get. This is the coupling coefficient that's varying on this axis. The dotted line, which you can barely see, is without the stochastic forcing in, so it was stable, past a critical point, amplitude suddenly jumped up and leveled off. That's some finite amplitude oscillation. Put stochastic forcing in, of course, just simply blew that picture out, where now the stochastic forcing, can get a finite amplitude ENSO down in the stable regime. Of course, you've got a stochastically forced ENSO instead. If you go increase the coupling coefficient, the model becomes more unstable, the amplitude tends to rise. Beyond a certain point, it doesn't really seem to matter anymore what you do with the coupling coefficient until at some point it falls off the edge and goes into a permanent El Nino or La Nina state, effectively. And you can play this game with other sorts of parameters. Here's one where you vary the depth of the thermocline. People have postulated that, I'll show a picture in a moment, that under greenhouse gas scenarios the depth of the thermocline is going to become shallower in the tropical Pacific region. I should really vary several parameters simultaneously, but so I think you get some insight just from varying them one at a time. Here's the amplitude of my ENSO again. If I make the thermocline shallower, I tend to get a slightly larger ENSO, much the same period in this case. Not very sensitive actually to the depth of the thermocline. If I vary over a reasonable range of values, I don't actually move very far on this regime diagram. The model seems much more sensitive to other parameters than it does to the actual thermocline depth. Okay, just wanted to mention something about ENSO and climate change in this sort of context. There's a recent review by Matt Collins and his colleagues that's appeared that sort of summarises some of the robust changes that have been predicted under greenhouse gas warming, and also, of course, they looked at their particular vision of what's going to happen to ENSO under these changes. Roughly speaking, the world warms up. However, it warms up more along the equator, particularly, than it does in other parts of the tropics, so you tend to get a bit more of a temperature anomaly situated along the equator. Partly due to reduced upwelling in the system along the equator. Reduced upwelling because most of the climate change simulations suggest a slowing down of the Hadley circulation and the accompanying Walker circulation, and they also suggest changes such as a flatter, slower, flatter, shallower equatorial thermocline. Now you hope that all these models will agree on what happens with ENSO under all these scenarios. They don't. It's something that's well known. The range of behaviour ENSO in all these models is really quite broad. Some increase it, some decrease it. Some don't change it very much at all. So these various robust features are having contrasting effects on ENSO. Some are tending to amplify ENSO, some are tending to decrease it. Each model is tending to pick up on different sorts of features. Didn't put it up there, but one feature that they seem particularly sensitive to is the surface exchange of heat. It's a particularly complicating feature for the ENSO behaviour.
But the robust change of a flatter, shallow equatorial thermocline, isn't that essentially a robust prediction of a move in the direction of a permanent El Nino?
Not necessarily.
A flatter thermocline, that's El Nino.
That doesn't preclude having an ENSO. It's not flat, it's flat Earth.
Right, but you sort of
Okay.
have more of a
All
permanent.
right, you might think, okay, a flatter thermocline, that's going to tend to reduce the likelihood of an ENSO occurring, but something else in the model is making ENSO more likely, is tending to make it more active. So there are trade-offs, I think, is what's really going on. And we really need to perhaps understand some of these trade-offs a little better.
So when you say flat, do you mean longitudinally flat or latitudinally flat? 'Cause
Can't see a piece of chalk. From east to west along the Pacific, looking at the thermocline, it's tilted, it's deep in the west, shallow in the east, and that's
You mean-
zonally flatter. Zonally flatter. In that particular comment, zonally flatter. And oh yeah, in the same review, of course, they illustrated what happens to all the different ENSOs in all these different models. And as I said, some go increase the activity, some decrease it, some don't change it much at all. So it's an important issue which people are very actively trying to figure out what's going on. All right, my time is up, so let me just summarise what I've been telling you about. I wanted to give some sense of where we are with seasonal forecasting systems in the sense that they make use of general circulation models in much the same configuration as they're used in climate model predictions. So there's quite a lot to be learned about the capability of climate model long-range greenhouse gas predictions from the behaviour of the seasonal range systems as well. And various bits of work have been done in the seasonal context, such as combining multi-models. Again, there's some overlap there with what people want to do with the greenhouse gas trend combination of information from various sources. Applications I didn't say too much about, but it's another sort of growing area where you want to leak output from something like a seasonal forecast model. The actual data from that you want to put into an application model, whether it's a crop model, dam storage model, or whatever, into some economic model. There's scope for developing all sorts of interesting mathematical models actually in this sort of link, which hasn't really been explored very much yet, with the ultimate aim of perhaps estimating better what's the actual value of producing all these forecasts. And the other part of the talk I just wanted to, by way of briefly describing one of the family of simple models to you, and raise the possibility, as has been done by Kim and Jin and others, using different sorts of simple models, the possibility of using simple models and trying to assess coupled GCM behaviour. Can you build a simulator, if you like, of a GCM based on a simple model, and then draw some sort of deductions about how your complex model behaves? And maybe some role as well in trying to perhaps understand in a readily understandable way, hopefully also the correct way, how these various changes that are postulated under climate change might be affecting the behaviour of ENSO in the future. And just one final, I'll leave that one on there. It's always this is what's been going on in the Pacific recently, and it simply shows you the sea surface temperature has been evolving from El Nino-like behaviour, a fairly rapid shift towards La Nina-like behaviour recently, and there are all sorts of interesting features you can see in these diagrams, like a bunch of fast Kelvin waves in response to various wind stresses in this equatorial strip. These are kind of fascinating diagrams to look at, but of course what everybody wants to know is what happens next, given that particular recent evolution of the tropical Pacific. This is an easy one actually, pretty clear that one's evolving towards a continuing La Nina. It's much more challenging to look at these diagrams under circumstances where there isn't quite such an obvious feature in them, and you look back at the past history of what's going on in the upper ocean and think, well, can we try and understand what's going to happen next? Okay, we have this range of forecast models, simple models, through to a couple of GCMs to try and help us understand what the answer to that question is. Okay, I really will stop there and take any questions.